I don't know if you'll remember back in algebra when your textbook and your instructor started talking about the properties of real numbers. For example, we said about the real numbers a and b that a, b, the product of these two numbers was also itself a real number, that the sum of the two real numbers a and b was also a real number. We said that a plus b was equal to b plus a. We said that a plus 0 was equal to a. We said that a times 1 was equal to a. Let's see, we said that a times b times c was equal to a times b times c. And we said that a times b plus c was equal to a times b plus a times c. I guess I need to add c to my list of real numbers here. And depending on when and where and with whom you took your algebra class, some of these may have been proved. I'm a bit on the fence myself about whether or not I should require proofs in homework or in quizzes or in exams, for example, in this course. But I don't want to focus too much on that here, but I do want to go over these properties because it's important that we know what we can get away with, basically. What I've got on the screen here is properties of real numbers. We need not a property of real numbers, but a list of property of matrices, or specifically of matrix operations, matrix addition and scalar multiplication. So I'm going to erase this list of properties of real numbers and operations on real numbers and replace it with a list of properties of matrix addition and scalar multiplication. We'll start with the assumption that the A, B, and C, capital A, B, and C, which is the common notation for matrices, but we're going to assume that those are matrices, but that all three of them are of the same size. Some of these properties don't work unless we set that restriction. All three of these matrices must be of the same size. And the letters R and S are going to stand for our scalars. All right, these are just real numbers. And what we can say then about matrices is that any two matrices, for example, A and B, when you add them together, it doesn't matter which order you add them together in. And the reason for this is that the entries in column 1, row 2 in matrix A and the entry in column 1, row 2 in matrix B are going to be added together. So they have to be the same size, and that's accounted for in this restriction that we have up here. But then once you know they're the same size, you just add the two you add the entries from the same position in the two matrices together to get a new number for the same position in your new matrix. So because, and I'll actually make a note of this here, because the addition of real numbers is what we call commutative, right? Because real number addition is commutative. T-I-V-E, there we go. And that's akin to what we were saying before. We said the number A and the number B, when added together, doesn't matter which order you add them in, you will get the same result. And the same is true for matrices. Okay, so that's one property. Another is that if you take the matrix A and you add to it the matrix B, you do that first, and then you add to that the matrix C, you'll get the same result if you add first B and C together and then add A to that. And the reason for that is that the matrix B plus C, when you add together the matrices B and C, you get a new matrix. And that matrix is made up of the entries in matrices B and C added together. And once you've got that, if you add that result to the matrix A, which also must be the same size, then you get the result of the two numbers in each position from B and C added together with the same number, the number in the same position in A. Well, if you add A and B together first, the numbers from the same positions in A and B get added together, and then you add the number from the same position in matrix C. So each entry in this left-hand side here, A plus B, add the entries in A plus B together first, and then add the entries from C. Those are going to be the same as adding together the entries in B and C first, and then adding that to A, right? So we say that matrix addition is associative. Okay, up here I could have said matrix addition is commutative. Okay. Another property says that if you take a scalar and you multiply it by a matrix, and then you multiply that result, this will be a matrix, right? We've scaled matrix A by 3 or by 1/2 or by some other number. If you take that new matrix and you scale it again, you'll get the same thing as if you had multiplied the two scalars together first and then multiplied the result by A. So in the left-hand side, in the case over here, we're taking every entry in the matrix A and multiplying it by some number. That's going to give us a new matrix where every entry is S times the entry in A. And then we're going to take each of those entries and multiply them again by R. Well, because R and S are real numbers, if we multiply them together first and then multiply the entries in A, each of which is a real number, then we're going to get the same result. So here we say that we have an associative property of multiplication. Okay. Another one of our properties is what we're going to call the distributive property of matrix addition, and that says that some scalar times the sum of two matrices is the same as if you took each matrix and scaled it and then added them together. That's called the distributive property of matrix addition. All right, again, the reason this works is because the sum of two matrices is another matrix. If you add the two matrices together, you're just adding the entries of the matrices together. And when you do that and then multiply each new entry in your resulting sum matrix, multiply each of those by some scalar, you're going to get a scaled version of this matrix, A plus B. If instead you multiplied everything in matrix A by R and everything in matrix B by R and then added the two together, you would get the same result. And this would be a good one to just check, give yourself a scalar of say 3 and some relatively small matrices A and B. You might want to do something like let R be 3 and then let A be 1, 2, 3, 4, 5, 6, and B, let me get my parentheses in the right place here. There's my A, and I want to add that to 0, 2, 4, 1, 3, negative 2. I just made those up. I'm looking for relatively simple matrices to work with, but I threw in a negative down here just to make sure that it works with that. And what I want to do here is do this arithmetic, right? Do this matrix addition and then multiply the results by 3. And then I want to check and see if what I get when I do that is in fact equal to 3 times the matrix A plus 3 times the matrix B. Okay, is that equal? I'm going to put a big question mark there. We are not, when we do this, we are not proving it. We are showing it for one case. If I feel like there's time at the end of this video, I will do the proof for one of these properties just so that you can see what the difference between talking about a property and convincing yourself that it's true and actually proving it. All right, so but this is not a proof. This is just an example of kind of a way to convince yourself that this property does in fact hold true. In fact, I'm going to erase that example because I have two more properties to try to squeeze on this same slide. So I'm going to try to do that. I'll erase this example and we'll keep going. Okay, our fifth property on this list is something called the distributive property of matrix scalar multiplication. It's not just the distributive property of matrix multiplication, because matrix multiplication is something we haven't talked about yet, and it's very different from scalar multiplication. But this property is true for scalar multiplication, and it says that if we take two scalars and add them together and then multiply some matrix A by this new scalar, this r plus s here, this is just going to be a new scalar, right? These are just real numbers. So if r is 5 and s is 7, then r plus s is just 5 plus 7, which is 12. And that's just a new scalar. And what this property says is that I can choose either to add the scalars together first and then multiply matrix A by this new scalar, or I can choose to multiply A first by R and then by S and then add them together, and you'll get the same result. So again, here you might let R equal 2 and S equal 4 or 5 and give yourself a nice simple matrix A to work with, and try it out. Try it for yourself. See if you can convince yourself that that's true. Okay, the last one on the list of properties for now, these are just properties of matrix addition and properties of scalar multiplication of matrices. The last one for now is called the additive identity, and that looks like this. A plus 0 equals A. You might think that seems really obvious, but you have to consider that we're not talking about the number 0 here. This is not the number 0. This is the 0 matrix. We specified way up here, let's see, up at the beginning here, that A, B, and C are matrices of the same size. We probably should make sure that we understand that the 0 matrix that we're going to be working with here also must be the same size as A if this is going to work. But that should not come as too much of a surprise, because what we're doing here is matrix addition, right? We're adding the matrix A to the matrix 0, or the 0 matrix. So if A is a 5 by 7 matrix, then in order for a matrix addition even to make sense, then the 0 matrix that we're working with must also be a 5 by 7 matrix. And the reason this one works is simply because every entry in the 0 matrix is a 0. And since we're adding together entry by entry, we get every entry in A plus the corresponding entry 0 is going to be the same entry in A. So entry by entry, ultimately we end up with the matrix A plus the 0 matrix is equal to the matrix A. And that's what we call the additive identity. It's equivalent, if you will, to the idea with the properties of real numbers, that a real number A plus the number 0 always equals A. That's the same thing. It's just we're not working with numbers in this case. We're working with whole matrices. Now, I'm going to number these. I'm not really fond of numbering properties or rules. Where did I get 5? There are 5. There are actually 6. 6 properties here. I must have missed one. I did. It's all the way up there. Starting up here. I started squeezing things together because I was running out of room. 1, 2, 3, 4, 5, 6. Those are the numbers assigned to these properties in the textbook that I'm lecturing from in this video. I'm not really all that bothered. I'm not going to call it property 1. I might call it the commutative property of addition. But I'm certainly not going to put a question on the quiz that says, you know, state property 3. I mean, that's right. These properties could be listed in any order, and in some textbooks they are listed in different orders. So to call one of these property 3 just doesn't make sense. It's worth knowing what they're called, simply because other people you're talking to will know what you mean when you say the distributive property of matrix addition. We say matrix addition because otherwise we could be talking about real numbers. So this is the list of properties, and I'm going to take a minute now and prove one of them. All right, let's prove the associative property of addition. The associative property of addition is the one that says that if you take two matrices and add them together and add a third matrix, you'll get the same result as if you add the second and third matrix together first and then add the first matrix. We're going to prove this, which is a little bit different than, actually it's a lot different than just convincing yourself that it's true. The first thing I want to do here is to establish a notation that I can use that's a little bit more conducive to doing this work. So I'm going to say let matrix A be notated or annotated as A sub I J in these brackets. And I don't know if you'll remember, but back in section 1.2, we established this notation. And what it does, or what it means, is that each entry, the ith row, jth column, is represented by a real number. So we're distinguishing here the matrix A from the collection of real number entries in the matrix A. And that notation is going to become really important because I know there are things I can get away with real numbers. I'm not so sure I can get away with them with whole matrices yet, but I know I can do them with real numbers. So I'm letting I'm changing the notation that I'm going to use here just so that I can use the properties of real numbers. I also want to let matrix B be B sub ij, and matrix C, I want to use the notation C sub ij. And then I can say, let's see, then A plus B, in parentheses, plus C, matrix A plus matrix B, do that addition first, and then we'll add matrix C to that. Using my new notation, I get the entries in matrix A plus the entries in matrix B. I'll do that first, plus the entries in matrix C, and I'll do that last. Okay, so I haven't done anything. I haven't expressed anything unusual here except to re-annotate or use different notation for my matrices. What I'm going to do now, though, is say that by the commutative property, sorry, it's not the commutative property, it's the associative property. By the associative property of real numbers, this is equivalent to A sub ij, the entries in matrix A, plus, because each one of these is a real number, right? Little a sub ij is a real number, and the brackets around a sub ij, around this real number representative here, the brackets represent the matrix, but the a sub ij is telling us we're looking at the entries in the matrix. So a sub ij plus, because these are real numbers now, b sub ij, I could add b sub ij and c sub ij together first, right? So it kind of looks like a little sleight of hand because I'm just changing the notation that I'm using, but in fact, I'm changing it into notation that allows me to talk about each of these terms as a real number, not as a matrix. Well, let's see, I'll put a period there, and then this in turn is equal to, well, I'm going to say equivalent to matrix A plus matrix B plus matrix C. And that's the end of my proof. Your textbook takes a little bit more of a prescriptive approach. It proves the property of matrix addition and scalar multiplication, which is the, let's see, which one is that? It is the fifth property in our list. It proves that one. And it just, it takes each step and then it says, the reason it gives, oh, that's the definition of matrix A, and then it does another step and it says I can do that step because the definition of matrix scalar multiplication lets me do that step. Proofs can be quite personal, and so you'll often see proofs that are a little bit more wordy than they are lists of properties or lists of things that you can do, lists of operations and lists of reasons. It sort of depends. My main goal in doing this proof for you just now is really that I wanted you to see one, and I wanted you to see that it's different. It can be different from the style that's given in the textbook. At this point in the course, I won't ask you to prove. I'm going to say that now. I won't ask you to prove one of these properties. That doesn't necessarily mean that I won't ask you later in the quarter, but for the moment, I'm going to say that I won't ask you on the Unit 2 quiz specifically, and anything leading up to the Unit quiz. I may give you some exercises that ask you to try proving something, but I will not assess you on it. I won't grade you on it. Okay? So that's it for this video. And let's see, I think we have one more video to do for this textbook section. Yes, we do. We have an applications video, but that one I will definitely keep on the shorter side.